Welcome back to the deep dive. We've got a stack of really interesting technical notes today that revolve around a concept that sounds a little like science fiction, but is actually just, well, it's just math, and some very specific geography.
It is. It's geography, but inside a computer's memory.
We're looking at exploit development today, but we aren't just talking about crashing a computer anymore. We're talking about the difference between, say, breaking a lock and actually picking it. Specifically, we're looking at stack overflows and remote code execution, or RCE.
Which is, really the holy grail of hacking.
Right. And the sources we have, these are technical notes on buffer overflows, on shellcode construction, memory manipulation tools like GDB. They paint this picture of something that is just incredibly precise. I think a lot of people have this movie version of hacking where someone just types furiously and yells, "I'm in." But looking at this, it feels more like watchmaking.
That's a great comparison. It really is.
Yeah.
Because if you just want to crash a program, a denial of service, it's easy. You just throw a brick through the window, you send way too much data, the program gets confused, and poof, it shuts down.
You broke the toy.
Exactly. But remote code execution, that's different. You aren't just breaking the toy, you are carefully taking the toy apart, rewiring it so it does something it was never meant to do, and then putting it back together before anyone notices.
You're taking a program designed to, store a username.
And you're forcing it to give you full administrative control over the entire system.
So the mission for this deep dive is to figure out how that rewiring actually happens. We want to get into the mechanics of the payload. But, okay, before we get to the weapon itself, we have to talk about the battlefield. The notes mention that for this specific technique to work, the program stack must be executable. That feels like a crucial prerequisite.
It is the prerequisite. To understand this, you really have to visualize how a computer uses memory. We have this stack. Think of it like a literal stack of plates in a cafeteria. When a program runs a function like, say, calculate this sum, it puts a plate on the stack with some temporary data.
And when the function is done, it takes the plate off.
It takes the plate off. Simple.
Yeah.
But historically, in older systems or the specific configurations these notes reference, that stack was treated as executable.
Meaning the computer didn't distinguish between data, like a shopping list written on the plate, and instructions, like a command telling the cook what to do.
Precisely.
So if I write delete all files on that plate and the stack is executable, the computer might actually try to do it.
If you trick the computer into reading that plate as an instruction, yes. Modern systems have defenses, things like NX bits or no execute flags to prevent this. They basically say, hey, nothing on this stack can be run as code.
But the exploits we're analyzing today are for systems where that door is left open.
The door is unlocked. The computer is willing to run whatever code it finds sitting there in the stack.
So the door is unlocked, but you still have to walk through it. And this brings us to the core concept here. The payload. I see this term everywhere in the documentation. Constructing the payload, sending the payload. It sounds so militaristic, but in this context, what are we actually building?
A payload, in this specific type of buffer overflow, is a very carefully crafted string of bytes. It's a package. And according to the technical breakdown we have, this package almost always has 3 distinct layers. It's a very dangerous sandwich.
I like sandwiches. What are the layers?
Okay, so layer 1 is the NOP sled, layer 2 is the shellcode, and layer 3 is the repeated return address.
Okay, let's go out of order, because that middle layer, the shellcode, sounds like the most important one. When I hear code, I think of, Python or C++.txt. Is that what we're injecting?
No, and that's probably the biggest misconception. You can't just inject text like print hello world because the processor doesn't speak Python. It speaks machine language.
Mine.
Ones and zeros. Well, technically, we represent it in hexadecimal to save our eyes, but yes. Shellcode is the raw, compiled instructions that the CPU executes directly. It's the native tongue of the chip.
And why is it called shellcode? Why not, virus code or exploit code?
Because of its traditional purpose. When you hijack a system, you usually don't want to run some complex program right away. You want control. You want a command prompt.
A terminal.
In the Unix and Linux world, that command prompt is called a shell. Usually something like binch.
So the code's only job is to pop open a terminal window for the attacker? That's it.
Precisely. Once you have that terminal, that shell, you can type whatever commands you want. Browse files, skill passwords, install other malware. The shellcode is just the battering ram that opens the gate.
The notes reference a file here, systemshell.cpp. It seems to show how a legitimate program would spawn a shell.
Right. And that source file demonstrates how a normal C++ program asks the operating system, hey, can you give me a terminal? The attacker's job is to take that logic, compile it down into a tiny little string of hex bytes, maybe only 24 bytes long, and then shove it into the program's memory.
And you don't always have to write this stuff from scratch, do you? The notes mention a database.
Shellstorm.org. It's essentially a library. If you need shellcode for, say, Linux on a 64-bit Intel processor, you go there, copy the hex string, and you're good to go. It's very reusable.
Okay, so we have the heart of the attack, the shellcode. But looking at the payload structure, we don't just put that code in by itself. We have this thing called a NOP sled. NOP. I have to say, NOP sled sounds like a winter sport for programmers.
It kind of is a sport, the sport of not missing your target. NOP stands for no operation. In assembly language, specifically by 86, it's represented by the value 0 by 90 or just by 90.
No operation. So it literally tells the computer to do nothing.
Correct. When the processor hits a NOP instruction, it just pauses for a cycle and moves to the very next instruction. It's a pass.
I'm struggling to see why you would fill your malicious payload with essentially blank space. I mean, space is tight in these buffers. Why waste it on doing nothing?
Well, think about the problem we're trying to solve here. We are blind. We're injecting code into a running program from the outside. We know the code is somewhere on the stack, but we don't know the exact memory address where it starts. It might be at address 0up-EBIR of L450, or it might be at 0up-BIR of BFF458. Memory is dynamic. It shifts around.
So if you tell the computer, jump to address 100, but your shellcode actually starts at address 104?
You crash. You just land in the middle of an instruction, the CPU gets confused, and the whole program dies. You get one char, and you missed it.
Okay, so how does the NOP sled fix that?
It makes the target bigger. So imagine you're trying to land a helicopter on a specific landing pad in the dark. That's hard. But what if you could pave the entire field around the landing pad so that if you land anywhere in that field, a conveyor belt automatically just slides you onto the pad?
That's the sled.
That is the sled. You put, say, 100 bytes of NOPs before your shellcode. Now, you don't have to jump to the exact start of the shellcode. You just have to jump to any address inside that 100-byte sled.
And the processor hits the NOP, says do nothing, goes to the next do nothing, and just slides all the way down until
it hits the first byte of your real shellcode, and boom, execution.
That is incredibly clever. It turns a game of pure precision into a game of probabilities.
It's a safety net. It's absolutely standard practice because guessing exact memory addresses is just, it's incredibly difficult.
So we have the NOP sled to catch us and the shellcode to give us control. The last piece of this sandwich is the repeated return address. We touched on this, but what is the specific function of this layer?
This is the trigger. This is what starts the whole process. So to understand this, we have to go back to the stack. When a function finishes running, it needs to know where to go back to. The computer stores a return address on the stack. It's basically a bookmark that says, okay, when you're done with this function, go back to the main menu.
And we are overwriting that bookmark.
Exactly. We are finding where that return address is stored in memory, and we are just smashing it with our own address. We are replacing go back to main menu with go to my NOP sled.
And why is it repeated? The notes here say we should repeat it multiple times at the end of the payload.
Right. Again, it's all about probability and alignment. In a 32-bit system, an address is 4 bytes long. If you just write it once and you're misaligned by just 1 byte, you corrupt the address. Repeating it over and over, creating a block of our return addresses, just increases the chance that when the computer looks for that return address, it sees the value we want it to see.
So it's a brute force approach.
It's a controlled brute force. We're just patting the end of the buffer to make sure we stomp all over that instruction pointer no matter what.
Okay, so we know what the weapon looks like. It's a sandwich of NOPs, code, and repeated addresses. Now, let's talk about how an attacker actually figures out how to build this, because the source material makes it really clear. You can't just guess the size. This involves some pretty serious detective work.
It's a math problem, a geometry problem, really. The first step is what the notes call the crash test.
Which is just sending a massive stream of data to the program, right? Just to see what happens.
Yes. You violate the program's expectations. If the program expects a name that's, say, 50 characters, and you send it 500 characters, and it segfaults, which means it crashes due to a segmentation fault, that is a telltale sign.
You've proven the bucket can spill.
Right. But a spill isn't enough. You need to know exactly which drop of water caused the bucket to overflow. This is where a tool mentioned in the sources, GDB PETA, comes in. It's a debugger with some really helpful Python enhancements.
And the process described here is fascinating. You don't just send 500 of the letter A, you send a cyclic pattern. Can you explain that?
Of course, if you send 500 A's and the program crashes, the debugger says, I crashed at address AAA. Well, that doesn't help you. You don't know which of the 500 A's caused the crash.
Because they all look identical.
Exactly. So GDD generates a unique pattern for you. It looks like A, B, B, C, 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 D, D, and so on. Every 4-byte chunk is unique. Now, you feed that to the program.
And when it crashes.
The debugger says, I crashed trying to read the address at pattern RKLP.
And because that pattern is unique.
You could just ask GDB, hey, where is RKLP in that pattern I sent? And it will tell you that is exactly at offset 140.
That is the aha moment.
Yeah.
That number 140 is the distance from the start of your input right to the critical return address.
Exactly. Now you have the measurements for your suit. You know you have exactly 140 bytes of space to fill before you hit the trigger.
Okay, so let's do the math. I want to walk through the specific example from the source because it really makes this concrete. So in their example, they determine they need a total payload length of, let's say, 144 bytes to get everything to align properly.
Okay, 144 bytes is our canvas.
And we know from our shellcode database that the specific binary code we want to run, the one that opens the terminal, is 24 bytes long. That's a fixed value. You can't shrink it.
Right, so 144 minus 24, we have 120 bytes left.
Then we have the return address, the trigger. On a 32-bit system, an address is 4 bytes, and the source suggests repeating it 5 times just to be safe and ensure we hit the spot. So that's 20 bytes of return addresses.
So the math is 144 total, minus 24 for the code, minus 20 for the trigger. And that leaves us with exactly 100 bytes.
And that 100 bytes becomes our NOP sled.
Correct. You put the 100 bytes of do nothing at the front, then the 24 bytes of code, then the 20 bytes of addresses.
And there's a note here about alignment. It says the length of the NOP sled plus the shellcode usually needs to be a multiple of 4. Why is that?
It's because the CPU reads memory in words. On a 32-bit system, a word is 4 bytes long. If your address is split across 2 of those words, like half in one chunk and half in another, the CPU just won't read it correctly. It's like trying to read a sentence where all the spaces are in random places. The meaning is just lost.
It's amazing how fragile this is. 1 byte off, and it's just a crash. 1 byte right, and you have remote control of the machine.
That is the definition of exploit development. It's understanding the system better than the person who designed it, down to the single byte.
So we've built our payload. We have our 144-byte string of doom. Now, how do we actually get it into the program? The source lists a couple of delivery methods, and one of them involves this really clever trick with a hyphen.
Ah, the interactive trick. Yeah, this is a classic gotcha.
So first, let's talk about the standard way. If the program takes an argument from the command line, arg-vi, you can just paste your payload there.
Right. If you run that vulnerable program payload, the payload goes right onto the stack. GDB can even tell you the memory address of that argument, so you hardcode that address into your payload. It's pretty simple.
But the second method is for when you are piping data into the program using Stretton. So this is when the program asks you to pipe something in while it's running.
And usually in a hacking scenario, you'd keep your payload in a file. Let's just call it payload.bin. And you'd use the cat command to push that file into the program. Something like cat payload.bin.vulnerable program.
But the notes say this fails. Why?
It fails in the most heartbreaking way. The exploit works, the stack is smashed, the shell code runs, the shell actually spawns. But then it immediately closes.
Why does it close if the exploit worked?
Because the cat command finished its job, it sent the file, it reached the end, and so it closed the pipe, the connection to the program. So when the new shell spawns, it looks at its input source and sees that it's closed. Just thinks, oh, I guess the user's done talking to me, and it exits.
So you pick the lock, open the door, and the wind just slams it shut in your face.
Basically. So you need a way to keep that pipe open.
And that's where the hyphen comes in.
Yes. You run cat payload.bin.program. That tiny little hyphen tells cat. First, send the file. Then switch to reading from the keyboard from standard input and send that too.
So it just keeps the stream alive?
Keeps the stream alive. It tricks the shell into waiting for you to type else or whammy. Without that hyphen, you have no interactive session at all.
Just a tiny punctuation mark making the difference between success and total failure? That is wild.
It's these little nuances, that separate a script kiddie from a real practitioner.
Now, there's one more layer of escalation mentioned in the sources. We've talked about getting a shell. But not all shells are created equal. What if we want God mode?
This is where set2it comes in. It stands for set user ID. In Linux, a program can have a flag that says, when this program runs, give it the permissions of its owner, not the person who is running it.
So if the system administrator, if root owns the program.
Then the program runs with root privileges, even if you, a low-level user, are the one who runs it.
Oh, I see where this is going. If I exploit a program that is situate root.
Then the shell that spawns inherits those permissions. You don't just get a normal user shell, you get a root shell. You have complete, total control over the entire system. You can format the drive, read everyone's emails, change any password.
The source material mentions a specific nuance here regarding binge, though. Something about a link to.
Yeah, this is a bit of environment-specific troubleshooting in the notes. Some modern versions of Bench, which is often linked to Bash, have built-in protections. If they see they're running with situate privileges, but the real user isn't root, they automatically drop those extra privileges to protect the system.
So even the shell is fighting back against you.
Exactly. The source notes that to make the demo work in their specific lab environment, they had to link Bench to Bench, which is a different shell that, in this context, didn't have that same restriction. It just highlights that even when you have the theory right, the specific environment configuration can still block you.
Always another hurdle to jump. We also briefly touched on 32-bit versus 64-bit. The notes we're looking at are primarily 32-bit. Does this still work on modern 64-bit systems?
The logic is identical. The math changes, of course. In 64-bit, the registers are larger. They're 8 bytes instead of 4. The memory addresses are these huge numbers. But the concept pad with NOPs, insert shellcode, overwrite the return address, that remains exactly the same.
It's the same recipe, just a much bigger kitchen.
Exactly.
So let's bring this all back together. We started with a crash, a simple error. We used GDB to find the exact byte offset of that crash. We did the math to carve out space. And we built a sandwich, a NOP sled to catch our landing, binary shellcode to spawn a terminal, and a repeated return address to redirect the program's entire flow.
And then we smuggled it in, carefully keeping the input stream open with that hyphen trick, to slide execution away from the legitimate program and into our own code.
It's so intricate, it's mathematical, and honestly, it completely changes how I look at software.
What stands out to me is the precision. I mean, when you look at the source code for these exploits, it's not random chaos. It's about understanding the architecture of the stack so well that you can manipulate it. It's knowing the rules of the game better than the referee.
And that leads to a really interesting thought. The source material briefly mentions that modern systems have defenses against this, like non-executable stacks. But we just spent this whole time learning how to bypass the very logic of the program itself.
Right, we didn't crack a password. We didn't find a logic error in the code like if password equals password. We attacked the underlying memory structure. We subverted the physics of the computer's world.
So here's the question I want to leave everyone with. We assume our software is secure because the logic is sound, the password check is correct, the firewall rules are tight. But if the computer can be tricked into reading data like a long string of NOPs as instructions simply because of where it sits in memory, what other fundamental assumptions are our systems making right now that are just waiting to be broken?
That is the question that keeps security researchers up at night. And it's why understanding these low-level mechanics is so vital, even in a high-level world.
Absolutely. Well, that's our deep dive on remote code execution. Next time you see a program crash, maybe you'll wonder, was that just a crash or did someone just find a new door? Thanks for listening, and we'll catch you on the next one.